Videos will be available again, okay, on the link. I will provide the link, so it will be there. Okay. Now, conductors which allow passage of current, insulators which do not allow the passage of current, semiconductors allow very small flow of current. Maybe small flow means what is the magnitude? Maybe in milliampere and microampere. Okay, what do you mean by milli? Milli means 10 to the power of milli means 10 to the power of minus 3, and micro means 10 to the power of minus
6.
Milli.
Nano is -9.
Milli means m 10 to the power of minus 3. Micro means mu. Okay, 10 to the power of minus 6. Nano means n 10 to the power of minus 9. Pico means P, that is 10 to the power of minus 12. Okay, keep this in the mind. Now, dielectrics. What are dielectrics? That which allows very, very small amount of current, especially in electronic devices, okay, like computers and all. Okay, we use semiconductors. Now, dielectric material or low material, it has polarity. Okay, has dipoles in it. Okay, dipoles. Material which have dipoles in it. Okay, material which have dipoles in it. Dipoles in it, and on placing this material in electric field, they orient. Okay, they orient in the field. They orient, that means they will align in the direction of the field. They align in the field. Okay, they align in the direction of the field. They align in the direction of the field. Okay, here material which have dipoles in it, and on placing this material in electric field, they align in the direction of the field. Means what will happen? Suppose this is the electric field. This is the electric field, and you are placing the material. What will happen? All the dipoles will align in the direction of the field like this. Suppose this material is having dipoles. There are so many material. Like the example for this is what? Mica, glass. Okay. Example for this is mica and glass. So keep this in the mind. I will give an example. Like suppose mica and glass, they are dielectric material. Also, they are known as the insulators. They are mica and gold. They are dielectric material, and also they are insulators. But wood and rubber, they are insulators, but they are not dielectric materials. Why? Because this material will not have, wood and rubber, they don't have polarity. They don't have dipoles in it. It's not compulsory that everybody is having a dipole. Okay. Whereas dielectric material means which have dipoles in it. And when you place that type of material in the electric field, they start aligning in the direction of the field. Understood? That's a special property of dielectrics. Clear? So that is why mica and window has that particular property. Is that clear? Now, so there is a statement: all dielectrics or insulators, but not all insulators are dielectric material. Understood now? All dielectrics are insulators, but not all dielectrics are insulators.
Okay.
Not all. Insulators are dielectric material. Yeah. Understood now? So that is a statement. Next is superconductors. Superconductors are there. They are that material, like the resistance I'm writing here. Okay, here I'm writing. So resistance is 0 ohms. Okay, resistor is 0 ohms. So means what? At temperature T is equal to 4 Kelvin. This Germanium owns. There is a scientist. Okay, Germanium owns. He found out this phenomena. He got Nobel Prize for that in 1969, I think. Germanium owns. This is a scientist who did this experiment, okay, on superconductors. What he did, he took a wire or a wire in the form of a ring, and he kept at a very low temperature. It is not possible at normal temperature. 4 Kelvin means how much? It is almost minus 269 degrees centigrade. It is not possible at ordinary temperature, ordinary conditions. Even in the freezer, the temperature is how much? Minus 10 or minus 20, not more than. If you go to ice cream freezers, minus 35 or minus 40, not more than, not less than. So this is possible only under certain conditions, at certain pressures and certain material, at certain with certain material, with certain like for 35, for 35 and 40, for 35, for minus 35 and 40, we use generally freon gas. But for this, we have liquid nitrogen, and there is a substance called gadolinium sulfate. There is a substance. With that substance, they tried to reach that minus 269 degrees centigrade. And because of that, at that temperature, the resistance of the wire will become zero. That means what? The current starts flowing continuously without non-stop, without stopping. Even he removed the wire, the electron was continuously moving in the ring because everything became standstill. Everything became standstill. So this particular phenomenon is known as superconductors. This is very important property because if this is successful, now we are doing, the Americans are doing, US people are doing research on superconducting wires. When we pass the current from one city to another city, like suppose at the transmission station, it is how much, 33,000 volts. But when it reaches the destination, it is only 11,000 volts. Means 22,000 volts of temperature is wasted. Sorry, of voltage or energy is wasted in only transmission. In only transmission means why? Because there is resistance in the wire. Why? Because there is resistance in the wire. If you are able to produce superconducting wires in future, that means what will happen? Yeah, with the same energy, you can light 3 cities instead of 1 city. Understood? So that much energy can be saved. Understood? And not only, if anyone is biology, you can understand. In bio, math. In biology, we have this, what we say, in biology, we know there is a placenta. Placenta is the connection between the baby and the mother, right? That is typically umbilical cord. Umbilical cord. There is a preservation companies are there. Umbilical, they preserve it. If you have to tell that company, so when the baby is born, these people will come with a box, and they will take that. Once the cord is cut, immediately the doctor will give it to these people, and he will take it to the company, and he will store it at minus 179 degrees centigrade, around minus 180. It is preserved there. This is like an insurance company. You have to pay annually or some 5 years like that. Some you have to pay some more. Like they store it. Suppose if the baby requires, if that person requires, like we don't know, or at a certain age, if requires any blood, to the same umbilical cord, but because umbilical cord is rich of blood cells, so they will make the blood from the same cord. Okay, there is a way to do it. So they will do it and they will supply it to you. But you have to give some time. Immediately they will make it. It means you are getting, the person is getting the blood from the same blood only. Understood now? So that is one of the important property. Like that, there are many applications of superconductors. But anyway, that is not in our that much into the deep in our syllabus now for time being. Okay, this is there in electricity chapter also. Okay, just to know the classification of the material, I just explained the superconductors and dielectrics. Okay, now classification we will see. The classification of semiconductors, then what are third group elements, fourth group elements, fifth group elements, we will see. Okay, what are valence electrons, valence shell, core electrons, and all we will discuss now. Is it clear? This thing? Okay, can I off the AC? Yes. Now, this is one of the interesting chapters, man. Actually, what happened is they deleted most of the chapter. Only up to diodes only we have. Actually, there were transistors. There are 3 configurations: PNP, NPN, and 2 configurations are there, and CE configuration: CE, CC, CB. In that only CE was there, and we have 2 types of transistor: NPN and PNP transistor. Once you study this, you will understand. When you go to higher level, you understand FET, FET, like field effect transistor, UFET, JFET, MOSFET. Many transistors are there. It's a family actually, big family. So once you understand transistors, again there are gates. Once you understand all these things, you will understand the manufacture of the chips. Yes, the motherboard we use chips. In your mobile phone we use chips. Okay, all this. So we can understand all this. But anyways, bad luck because they removed all the actual stuff they removed. So very interesting, Very interesting because we need after that communication was also there. They removed the communication also.
chapters.
The most of the chapter is deleted. Actually, transistors, configuration of transistors, types of transistors, logic gates was there. Again, there were communications. Huh?
We're studying logic gates in
Computer science. Because you know computer science, because your subject is computer science, you are able to know. But otherwise, as a physics student, you would have known more than that. Okay. Anyways, maybe this year maybe they may add, but now they added again, but they again blocked that site now. The link is not working. They said full portion when I downloaded, but now that link is not working. Means when you go to CBSE academics to download the syllabus curriculum, it's not showing anything. Maybe they are still working on it. Maybe they are still changing, or they want to use the old one. We don't know. I don't know how it will go. Okay, anyways, so is it clear now the types of material? Okay, so now here we will start with third group element. So first the classification we will see, and before going to that we will see. Okay, first classification we will see semiconductors classification. Yeah, semiconductors. The classification is like this. We have P type and N type. Sorry, sorry. What is that? Extrinsic and intrinsic. Yeah, intrinsic means pure. Intrinsic means pure semiconductors, and extrinsic means impure. Okay, extrinsic means impure. Impure semiconductor, pure semiconductor, and impure semiconductor. And again, extrinsic we have two types. That is P type and N type. P type semiconductor and N type semiconductor. Okay. And this is pure means example for pure semiconductor is germanium and silicon crystals. Germanium and silicon. Okay. Yes, semiconductor material qualitative ideas on this. Yeah, I know. This is the. They only removed Zener diode, which was again useful diode. Okay, Zener diode is used as a voltage regulator. In most of the electronic appliances, they are using Zener diode, but they removed that also. Very important one also. With what idea they have, but the problem is when the syllabus is reduced, the complexity of the paper will increase. When the syllabus comes down, complexity of the paper will increase. This is the problem with the reducing portions. So you have seen, see, the case study was very simple, but that was from current electricity. You have seen, right? No one expected that it will be from current electricity, and that also only what he asked, the power and all. That's very simple things that he asked, right? Yes. Now, next is here we have we'll study about that is core electron. Okay, what is a core electron? What's the definition of core electron? Electron which is close to the nucleus. Okay, electron which is close to the nucleus. Which is close to the nucleus is said to be core electron. What is a valence electron? What is valence electron? Yeah, very good. Electrons in the outermost orbitals. Electrons in the outermost orbitals. Outermost orbitals are known as valence electrons. Sorry, outermost orbitals are known as valence electrons. Okay. Next we have bands. Okay. We have valence band, conduction band, forbidden band, and all. Okay. What is a valence band? Okay, to make you understand this, suppose example, like if you are taking example, I'm taking only one example. The example, like suppose if you take sodium, what is the atomic number? Atomic number is 11, right? And here it has a configuration 1s2, 2s2, 2p6 and 2p6 and 3s1. Okay. So what is happening? This is the configuration of neon, zero group elements. 1s2, 2s2, 2p6 is the configuration of the neon, means zero group element. They will not participate in any chemical reaction, or they won't participate in any party, or they won't give party, or they don't go in any party. Such type of people, zero group elements. Okay, but 3s1, this is one extra electron. Suppose if there is one atom, there is one electron, right? But if I am taking 1 gram of any substance, 1 gram of a substance, there will be millions of atoms, right? If I take, but that can be again calculated using Avogadro number and all. That is the method is there. Okay, Avogadro number is there. Like the 23, suppose here we have for sodium, the atomic mass is 23. Means in 23 we have Avogadro number of atoms. Means 10 to the power of 23 atoms are there. 6.2 into 10 to the power of 23 atoms are there. But in 1 gram maybe there will be million atoms will be there, right?
Yes, sir.
Approximately maybe more than million also, we don't know. 10 to the power of 23 means more than millions and billions. Okay. So, but if I take 1 gram of sodium, there can be at least a million atoms. For one atom, there is one electron. For million atoms, there will be million valence electrons, right? Understood?
Yes, sir.
So for that, he could not explain that properly. So for that, he said that instead of saying electrons and all, he said a band. Now, he named it as a band. Got it now?
Yes, sir.
Instead of saying a group of electrons, group of valence electrons, group of valences and all, he's not mentioning that. He's saying in simple words, he said band. Understood now? So now he said valence band. Got it now? Valence band. Valence band means band formed due to valence electrons. Due to valence electrons. Band formed due to valence electrons is known as valence band. Understood? Now there can be million, billion. Okay, no need to worry about it now. You take 1 gram, you take 10 grams, you get 100 grams, 100 grams. It doesn't matter now. Okay, you mentioned it now in simple words. Clear? See, I mentioned Ramadan month. Automatically, many restrictions will come into picture. You cannot go. No one can sit in the restaurant in the daytime and you can eat. Okay, and no one can drink in front of the other people. There are some restrictions. Automatically, things will come into picture, right? Same way. So valence band means what? Band formed due to the valence electrons. Now, next comes what? Next is for conduction band. Okay. Next is conduction band. Conduction band means what? Suppose electron has to flow from one point to another point. So the electron has to come to suppose a player is there, man. A cricket player is there. All total 11 players are there in the team. Now 2 are on the pitch, they are playing, and 9 are remaining there. One, okay. So the cricketer has to come and so he has to make the run. Means what? First he has to come on the pitch, right? First he has to come onto the pitch and then only he can play, right? The same way, electron from the valence band has to come to the higher band, that is conduction band. Then only the electron flow will take place. At valence band, electron flow will not take place. Okay, valence band, it is ready. Like the batsman is ready, right? He's wearing the, what is that? He's wearing, yeah, the caps and all. He is wearing everything. Helmet is ready. When the fellow is out, then he will be ready to go on the pitch, right? The same thing. Now conduction band means what? Band higher. Okay, the next higher band to valence band. Okay, the next higher band to valence band is said to be conduction band. Okay, so the passage flow of electron takes place here in this band, conduction band, not in the valence band. Okay, in simple picture now, what exactly it is. So we are drawing an energy level diagram now. Okay, for this we are drawing energy level diagram. How is energy level diagram? We'll just draw like this, a simple band like this. Okay, so this we write VB, this we write CB. Okay, and this is energy. We write in electron volt or something. Okay, energy in electron volts or joules also we can write. We have already a relation between the electron volt and joule. Okay, what is that? 1 electron volt is equal to 1.602 into 10 to the power of minus 19 joules. Okay, this is the value of 1 electron volt. Keep that in mind. This is only the charge of electron. Joshua, are you able to see the board properly? Oh, okay. Is it clear? Oh, okay. Now here, this is the valence band, conduction band. The next, the gap between both of them is said to be energy gap. Okay, this is said to be energy gap or forbidden band. Okay, that gap is also, there are two names for this: forbidden energy band or energy gap. Okay, so I'll write here. So now here we have energy gap. Energy gap or forbidden energy band. energy gap or forbidden energy band. Okay. So what is the meaning of this? The gap between valence band and conduction band. The gap between valence band and conduction band is known as energy gap. Okay, or forbidden energy gap. So see, what electron first, suppose if the conduction has to take place, the electron has to jump from valence band to conduction band first. Understood? Electron has to jump from valence band to conduction band. So suppose if it is very narrow, it becomes conductor. If it's very wide, it becomes insulator. If it is little, then it becomes semiconductor. So that is how they have classified the material again. They have classified the material. Now again they brought a picture called Fermi level here. What is a Fermi level? Which is very important. Actually, he did not say Fermi level. He said ECEV. Here, energy of the conduction band, energy of the valence band. He said like that. Okay, let us discuss that also. But first, is it clear first? What is core electron? Electron which is close to the nucleus, and valence electron, electrons in the outermost orbitals is said to be valence electron. Because when there are, if I take 1 gram of material, there can be millions of atoms. So for that, instead of saying valence electron, million valence electrons, we are saying a band. A band formed due to the valence electrons is said to be valence band, and the next higher band to valence band, where the conduction, we can also add where the conduction takes place. Okay, next higher band to valence band, where the conduction takes place is known as where the conduction takes place. Okay, where the conduction takes place. Okay, that is known as conduction. I'm not writing the textbook language. I'm not using textbook language for now because that is something different. Okay, for now I'll write simple. Then we will enter. Once we enter into the topic in detail, then we'll discuss. First of all, you should know the terms. Then only you can understand the theory. Okay. Now here, now we'll go to third group element, fourth and fifth group elements. Okay. Now, and how is the bands and all? See, suppose if I speak about a conductor. Okay, if I speak about a conductor, how it is, you know, the conduction band and the valence band, they both overlap. Okay, they both overlap. See here, the conduction band and the valence band. The valence band and conduction band, they overlap. Okay, they both overlap. So this is said to be what? Conductor. Is that clear? And conductor, they overlap. So you need not give any energy, man. Just apply potential difference, electron starts flowing. Like suppose this is the wire. You apply the potential difference, current starts flowing. It's because it's a conductor. Okay. So no need to get extra energy because they're already ready. Just apply potential difference, current starts flowing. But in semiconductors, if you speak about semiconductors, in semiconductors, how it is? Suppose there is a small gap. There is a small gap between the valence band and conduction band. That gap is how much? Energy gap. That gap is equal to approximately 1.1 electron volt. Okay, just above 0.7 to 1.1 electron volt. Or we say it is less than 3 electron volt. Okay, we say less than 3 electron volts in general. Okay. Now the third one is what? Insulators. If you speak about insulators, the gap between them is very high. That is greater than 3 electron volts. Okay. So rubber and wood is the best example. Again, I'm telling you, don't think that rubber and wood is every time a insulator. No. Why? If the rubber and wood is wet, so do we need to apply energy? Yeah, little energy is required. Little energy. How much energy? Little means how much? Maybe 0.7 electron volt, 1.1 electron volt. Little energy is required. Okay. So, but surface insulator, do we need to apply energy? If you have to apply very high energy for insulators. Example I will give. See, I am taking wood and rubber is a insulator. Dry wood and dry rubber is a perfect insulator. But if I pour a drop of water or few drops of water, that insulator is no more, the wood is no more insulator, it becomes wet. So suppose you are standing on a dry rubber and you switch off, not a problem. But if it is a wet, there is a possibility of getting a shock because it is no more rubber is no more a insulator, it became a conductor now. Understood? The water droplets are ready to conduct the electricity now. Even the wood, wet wood also. Understood now? So this is the problem. So that is why in India, like here also, or in India also, whenever the branches of the tree enter the wire and all, they cut it. No, because when there is a rain and all, if you standing and touch nicely, then directly FD, current destination. Understood? Current will pass to the wood. Within 9, no, nothing will happen. My teacher told, like when I was small, like he told it's an insulator, so I will nicely stand. No, it's not, no more, because it's wet. Right? When water flows, automatically what happens? It's no more a insulator, right? So that is why they cut the branches, because people don't know. That is the reason. So yeah.
According to this theory, so that means even insulators conduct electricity but in a very low rate.
Yeah, exactly. That's what I said. So that is why when you give very high energy, when you give very high potential energy or a potential difference, then there is a possibility that even the insulators also can become conductors.
So, but then if you give very high
But
energy to wood, then it will burn you.
No, that's what I'm saying. That's what I'm saying. That's why I give an example of wet wood and wet rubber. Understood? Generally, dry wood and dry rubber, they don't conduct any electricity. Understood? So example I will give, one more example, nice example I will give. Now suppose we say that birds, best you know that birds are they are singing they're singing song, nicely dancing. That is, they sit on the wire, right? They hold with the paws and nicely they are sitting and singing song. Nothing happens to the birds. But when I catch a wire, I will get a shock. No problem. Now says, okay, sir, because there is no contact between the bird and the ground, that is the reason. Yeah, we say like that, right? There is no connection between the bird and the ground. So that is the reason it is only connected to the wire. So that is the reason it is not getting any shock. Perfect. But now, suppose there is a person who is hanging on the wire, on the live wire. He will not get any shock. But if there is humidity in the air, or there is a rain, like there is humidity or moisture in the air, is gone. Why? Because that molecules in humidity, the molecules, water. Humidity means what? Water molecules or water content present in the air. That will make the passage from this body to the ground. So automatically current will flow and this one is gone.
So, but if these birds sit on the wire like during rainy days, will they also get it?
Still, the body is not in contact with the ground, right?
So during humid days.
Humid days also, but when compared, the body is very, very small, right? And the gap is very large. You understood? Suppose if the wire is very close to the wall, these two wires or whatever the wire is there, and the body is sitting, and the wall, suppose there is a wall or some house is there, and the wall is there, and it is raining. Maybe again it can catch fire. That maybe there can be a shock.
Why don't they insulate the wires?
Why they?
So, why don't they insulate the wires?
Yeah, but now they are insulating the wires. Now, see, the problem is insulating wires are expensive again. But now they are doing in India now, especially in the cities and all, they are taking insulating wires only. First of all, headache is with the the overhead cables. In India, there is a overhead cables, right? Many countries we have overhead cable. Here we don't see any hanging wires here. We don't have any overhead cables here. Only somewhere in the interior or somewhere only for high tension towers you have that overhead cable. Otherwise, we don't see any overhead cables here. All wires are under that is buried under the ground, and those cables are well insulated and they are expensive actually, highly expensive. These cables, overhead cables, which we use in India, is not expensive because it's without a insulator, right? Still, the people live there, like especially in cities and all, where the buildings are very close to each other, they request the electrical authorities to change the cable. So there they have placed again insulated cables. It comes with very highly insulated cables. Even if it has, nothing will happen. Understood? It is there still, but you have to request again to those people, or sometimes you need to pay the money also. The community people have to pay money to get it done. That is the situation in India. Okay, but here not a problem. Here it is completely underground and it is well insulated cable. And also Indian headache is we don't know when they are going to dig the ground. That is also a problem. Yeah. Here it is not like that, right? Here we have SIGA, and it's a complete one department, right? Electricity, water authority, and gas authority. This is one department, so it's not a problem. They know the lines where exactly like water pipeline is there, where exactly these current lines are there, where exactly the optical fiber lines are there, where exactly the drainage pipelines are there. They have the picture, but India is not like that. Okay, so this comes headache. So that is why it is better to be there. Overhead cables are better, but like good cities, like where there is a like new colonies in cities, they are going with underground cables on. They are going properly with them because they have proper planning over there. Yeah, management is there, like especially the communities and all community areas and all. Okay, so that was about semiconductors and all. Got the idea now?
Yes, sir.
So it should be more than 3 electron volts. Sorry, less then only means we have to apply very high energy. Then only what happens? The current will flow. Okay, so don't think that it's not possible. Generally, it's not possible. Okay, but still, if you apply more than that, maybe the little current can flow. Okay. Now, next one is what? Next we will discuss about. Okay, we'll discuss about the group, the third group, fourth group, and fifth group elements. In periodic classification table, we have 3A group elements. 3A, that is 13th group element. Yeah, 3A, that is 13th group element in the periodic classification table. Periodic classification. Yeah, that is what boron, aluminium, gallium, indium, and thallium. Okay, and then fourth group element, that is said to be again 14th group. Sir, why do we need to study in all this? Correct. Chemistry already has so much. Correct. Now you are bringing in physics. Why? Because there are like suppose LED is a simple example. I will give. LED is a light emitting diode. LED, we have green color LED, we have orange color LED, we have red color LED. How is it possible? Again, this is a chemical composition. You understood? Again, there is a chemical composition. It depends upon what type of composition you take. Okay, how the color changes. Even in the tube light also, you have white color tube lights, you have green color tube lights. Yeah, what is that? There is a gas. Because this is mercury vapor gas, inside it we are getting white color. But if there is some other gas in it, then we can change the color. We have orange color, we have blue color, green color tube lights are also available. It depends on the gas present in that inside. Okay, so now. Fourth group element. What is that? Carbon, silicon, germanium, and tin and lead. Tin and lead.
So arsenic, bismuth, carbon, right? Oh, that's 5.
The fifth group element. Fifth group element is 15th group. Okay, in periodic classification table. In the old one, we say 5. Okay, this is what?
So this arsenic.
No.
Antimony.
Nitrogen, arsenic.
Antimony.
Nitrogen, arsenic. Arsenic, antimony,
and bismuth.
No.
So antimony is SB.
Wait. Phosphorus, arsenic, antimony, and bismuth. Here we don't take these 3 we don't take because these 3 are gases, and these 3 we don't take because these 3 are radioactive. Only these are only involved in the involved in the preparation of the semiconductors. Now these 3 are pure semiconductors. Okay, silicon and germanium, they are pure crystals. Okay, now we have a definition that is certificate doping. Doping means what? Addition of impurity to a pure semiconductor. Addition of impurity. Addition of impurity to a pure semiconductor. Then people started asking, how much impurity? Is it like in adding milk to water in India? Adding milk to water or water to milk?
So water to milk.
In India, they add milk to water.
Milk to water.
It's what?
There is more water.
More amount of water and less amount of milk. Okay, here we are. If you once using your milk and you go to India, only in the dairy farms only you get a good milk. Okay, otherwise no. If you take milk from other end, they will it's like, not, we cannot say even low fat milk also. Okay.
It's no fat.
Low fat. So, yeah, addition so it is how much it is? It is like added like 1:10 to the power of 8, it seems. The impurity is 1 molecule to 10 to the power of 8 molecules. Means that much impurity is added. Okay. Very less. Impurity means doesn't mean that lot of stuff is added. Okay. So doping means addition of impurity to a pure semiconductor. Now we will see how this thing is formed. A p-type and n-type semiconductor is formed. Okay. We will see now how a p-type and an n-type semiconductor is formed. Okay. Now, so we have p-type semiconductor. So let's start with n-type semiconductor. And n-type semiconductor, what we are doing is we are adding 4th group element to the 5th group element. Okay, means what? We are taking 4A group element and the doping element is 5A. Here 4A is a pure one, 5A is the impure one. So suppose I am taking example, the 5A is, maybe I will take here 5th group, let it be X. Okay, so let it be having 5, let it have 5 electrons in the outermost shell. Okay, 5A means what? It has 5, this has 3 electrons in the outermost shell, this has 4 electrons in the outermost shell, and this has 5 electrons in the outermost shell. Okay, is that clear? 3, 4, and 5. Now this is X is a 4th group element. It has 5 electrons in the outermost shell. I'm taking Y. Y has 4 electrons. This is a pure semiconductor. Okay, so again this has Y again has 4 electrons in the outermost shell. Again here Y 4 electrons in the outermost shell. Here also Y 4 electrons in the outermost shell. So what happened? This is the bonding took place. This is again a bonding. Okay, this is again a bonding. This is again a bond, forms a bond. Now this is the excess electron. This excess electron is known as this will give rise to excess electron, that is said to be excess charge carrier. So that forms a n-type semiconductor. Means for every combination we have 1 electron. Yeah. So in n-type semiconductor, semiconductor, charge carriers are electrons. Charge carriers are electrons. Is that clear now? In n-type semiconductor, charge carriers are electrons. Okay. In n-type semiconductor, charge carriers are electrons. Okay. So for every 1 combination, we get 1 excess electron. Okay. Now we'll go to p-type semiconductor. Then we can discuss about the Fermi level and all. And there was a question here in the boards. That question was, he is asking how a pure crystal is different from the n-type and p-type semiconductor at ordinary temperature. He is asking how a pure semiconductor is different from the impure semiconductor at normal temperature, at normal 25 degrees centigrade. That means you want to link now valence electron with the temperature concept. That question is asked in one of the board exam. Okay, students could not understand exactly what it is. Maybe they wrote something and they left off. Okay, we'll discuss that concept. Okay, the temperature dependence. Okay, now what is happening with 1 degree rise in temperature? Suppose there is a material, pure material, and when we increase the temperature, when we increase 1 degree rise in temperature, what exactly happens? How many electrons will jump to the higher energy level, and what is causing the conduction? That we have to discuss. Okay, we'll see all this. One of the important concepts. Okay, let me first finish up the p-types and the p-type and the Fermi level and all. Then I'll explain that also. Now, yes, Arham, how are you? Arham and Hashim.
I'm good, sir.
Yeah,
How are you, sir?
didn't reach. Can you message him? Can you message Aaron? I don't know where he is.
He had messaged me. I messaged him back, and he appeared offline on WhatsApp.
Okay. Maybe he's on.
I think he's on his way.
Oh yeah. Where is this guy? Ashas?
Asha's Sai seems to be, I think, in another meeting.
Okay, okay.
It's
No,
showing me
no.
that he's in another meeting.
Okay, we'll go ahead with Peter. Just wait for some time.
Okay, sir.
You continue with that, Hashim. You continue with your work.
Sir, I didn't give any.
Yesterday's we did know that subtraction and multiplication property, associative property.
Yes, sir. Yes, sir.
Continue with that associative property. Okay. Now, p-type semiconductor. In p-type semiconductor, we are taking fourth group element. The fourth group element with the third group element. Okay, the doping element is 5A, 3A. Now, suppose here we have X, that is what? It has 3 electrons in the outermost shell. And Y has again 4. 1, 2, 3, 4. So this is 1, 2, 3, 4. Again 1, 2, 3, 4. Again 1, 2, 3, 4. So this is the bonding, and we lost one. There is a vacancy. Okay, this is said to be hole. This is said to be a hole. Okay, for every one combination there is a hole. Keep that in the mind. Hole is the vacancy part of electron. Hole is the vacancy part of electron. Okay, vacancy part of electron. How to explain this actually? We say electron current, hole current. Is it really possible? Electron current is simple to understand that there is flow of electrons.
Good afternoon, sir.
Yeah, good afternoon. Now see here. See, try to understand this concept now. Now suppose, example, see here. Sajid. Now this chair is empty here. Okay. Like think that with 3 are electrons. Okay. This is the vacancy now. This is the vacancy. Now I tell you to move ahead. So he moves to this chair. This is said to be electron current. Now what happened? We started making a vacancy on the backward direction, right?
Yes, sir.
Actually, are the chairs moving?
No, sir.
Chairs are not moving. Electrons only are moving. Now what happened? A vacancy was created when he moved to this chair and you moved to this chair. There was vacancy was created. That is said to be a hole. That current, the flow of that, when the electrons are moving in one direction, holes are moving in the opposite direction, right? Actually, they are not moving. They are created at that. When electron is moving, a hole is created backward.
Yes, sir.
That is said to be hole current. Understood now? Actually speaking, electron, when we say positive charge, we think that it is a proton. But positive charge is not proton. It's a deficiency of electrons. Understood? Positive charge means deficiency of electrons. Less number of electrons is said to be positive charge. We have to explain in that way. But students think that they are protons. Protons cannot come out of the nucleus. Here also, when we say holes and electrons, it doesn't mean hole is a proton. Then why did we give positive charge? Because it is exactly moving in the opposite direction. We told it is a positive charge. Understood now? Is that clear? Please try to understand this concept. Hole current, whenever I say hole current, sir, will the holes move? No. Actually, when electrons are moving in one direction, holes are created in the backward direction. Understood? Understood, Joshua? So we have p-type and n-type. Then we have to discuss about the Fermi level and all. I think
Fermi level is that
one line
high
will be
energy
there. Line. Why there is a line? Fermi. See, did you complete this? Just 2 minutes. Okay, let me finish off this part. Then I will start with you. Now. This is the one. Yeah, this is the one which decides the flow of electrons. Okay. Now let me draw one. Okay, so here this is what this is. I'm drawing a valence band and conduction in simple parts. That is valence band and conduction band. I drew. Okay, this is the energy which is measured in electron volts. Okay. Now this gap is said to be energy gap. Okay, this gap is energy gap, and again energy gap of germanium is found to be approximately 0.7. What is that? 0.7 electron volt or volt? Think about it.
volt.
Is it volt or electron volt? There are two situations in PN junction diode. In PN junction diode, when we study PN junction diode, the depletion region is 0.7 volt. but here it is 0.7 electron volt. This is only for one electron actually. This electron
So
volt.
what is the difference between electron volt, joule, and volt?
Electron volt. See, okay, very nice question. Now this is electron volt, but you know one joule, one electron, like one electron volt is 1.6 into
Minus 19.
10 to the power of minus 19 joules. Means what? One electron volt is much lesser value than a joule, right?
Yes, sir. Yes, sir.
Very, very small value is electron volt. Understood now? If I want to create 1 volt means we use the V is equal to W by Q. Okay.
Yes, sir.
So 1 W is what I am speaking about one. So work done by charge. For one charge, how much energy is used?
Yes, sir.
That means what? Volt is a bigger value, right? Right.
Yes, sir.
So you got it now.
So W is equal to VQ.
W is equal to VQ. Yeah. That much of work is done. Understood now?
That's why it gave EV.
Understood now?
Yes, sir. Understood.
So okay, we'll just try to understand this. What is that? So actually, in suppose now I am going to first N-type material. Then I will discuss about a P-type material. Okay, energy gap. Okay, energy level diagram. I'm drawing energy level diagram. So for both, okay, energy level diagram for both. This is for energy in electron volts. Now we will discuss about this is for energy gap. If you are speaking about a energy gap, what is that for PN junction diode? There it is for germanium. It is 0.7 electron volt. Sorry, not volt. It is only volt. And for silicon, it is breakdown voltage. It is actually 1.1 volt. Okay, that's breakdown voltage. We have threshold. What is it? Cutting voltage. We have two concepts here: cutting voltage and breakdown voltage. There we will discuss this 0.7 and 1.1. What exactly it is. Okay. For timing, just keep this in the mind. Later on, I will discuss this. Once I start explaining the formation of PN junction diode and the characteristic of a PN junction diode, there I will explain in detail. But for time being, just we have this is valence band and conduction band. The gap is how much? The gap is energy gap. Okay. So now, this is I'm taking a P-type material. So here we have a P-type, N-type, and P-type material. Okay. Now here, if you speak N-type, this this is a dotted line. This dotted line, he says EV or EC. He wrote in your textbook as EC and EV, energy of the conduction band. But I am writing in a Fermi level. Okay, if this level is said to be Fermi level in simple words. Okay, but in your book he wrote EV and EC, some notations like this he used. Okay, understood now. Now actually, why this here in P-type semiconductor, this line is very close to this valence band, and here this line is very close to conduction band. What's the meaning of that?
So what is this line?
This level is a Fermi level. That level is said to be Fermi level. What exactly it is? I will tell you. See here, in N-type semiconductor, it is rich of electrons, right?
Yes.
It has excess electrons. In P-type, it has deficiency of electrons. More number of holes. Okay, more number of holes and less number of electrons. Here, it has more number of electrons. Exactly opposite. So what is happening? Here electrons already they are ready. When you speak about this one, electrons are already ready here up to here.
Yes, sir.
Just if you give little energy, it will jump here.
Yes, sir.
But whereas here in P-type semiconductor, it has lot of energy. We have to give more energy to jump from valence band to conduction band in P-type semiconductor.
Sir, but then electron and holes are oppositely charged. Why do they need to give more energy?
Electrons and
So electrons and holes are oppositely charged.
oppositely charged.
So why is there the concept of Fermi level? Then why is there why do they give extra?
Fermi level means it's like a margin, we can say. It's like a margin. You can say like a border or like a margin where, like suppose that margin is very close to conduction band in N-type,
Okay.
and it is away from conduction band in P-type.
Okay, sir.
Understood? So here what is happening, if the conduction has to take place in P-type, in N-type semiconductor, you give little energy, that is enough.
Okay.
But whereas in P-type, there are holes are more, electrons are less.
Oh yeah. Okay.
So what is happening? It's like this is full of
You have to
water.
give more energy.
Like this area is full of water, and this has shortage of water.
Yes, sir. Yes, sir.
So you will save your water, right? Very difficult to get water. That's such type of situation.
Okay.
Got it. So that is why he told there EC and EV, but I want to make it little simple. That's a Fermi level actually.
Understood. This level is like, so at that level the electron stops.
No, the electrons are ready to that point now. You little energy, like suppose this land is very fertile and lot of water is there. Water is only at 10 feet itself. Just drill up to 10 feet, you will get water. In drought area, drill up to 300 feet also, you will not get water. You understood now? Such type of situation it is. Okay. So we are trying to only explain with the analogy. Directly, we cannot explain this thing. Okay. So we will stop here for today. Okay, we'll continue again tomorrow with the PN formation of PN. Very interesting chapter, formation of N type, P type. Actually, I because I was teaching electronics before in a PG college. So electronics and semiconductor electronics, microelectronics, microprocessors, and integrated circuits and all. So very interesting. This is only the beginning of the thing. Very nice. Completely applicative actually. Completely applicative. What was applicated with the remote? So